All right, so thank you very much for the invitation here. I'm very happy to be here. So I'm going to tell you about statistical physics approaches to a problem in generative AI, and we introduce diffusion models. As I said, I count on Eric to introduce the diffusion model, and maybe I should say also that to acknowledge my collaborators, so Mark Nezar, which is collaborating in all the works that I'm going to tell you about, and then Tony Von Erwal, Valentin de Bortoli, and Raphael Ufan, who collaborated to different parts of the work. All right, so what is the, so in generative AI, there are different things. And so there is a part of generative AI that generate images, sounds, and videos. And this is based on something which is called diffusion models. And so diffusion models is really the state of the art in generating images, video, audio, and 3D scene. They are used in many applications, well, from text to image. So you can write, for example, I want an image of an angry bird, and here's what you get. And they're also used in science, and you will know about this in the next talk by Eric about the application of generative models to do, let's say, better sampling, if possible, or to produce complex dynamics, for example, like in this case of Lagrangian turbulence done by Luca Biferrada et al. Or, for example, to compute entropy production. Again, you will hear Eric about this. So how diffusion model works, and so the nice thing about diffusion models is the reason why also I started work on this, and I think physicists find them, many physicists find them very interesting, is they're really based on physical ideas. So what you do is that, let's say, well, you have a certain training set, a set of images. Images, you can think just vector, they are just vector in D dimension. This is the, all the pixels are packed into this vector. So you have n data. And so for each image, so for, let's say, for each data, you run a Neustadt-Uhlenbeck process. So where X, so it means that each, let's say, pixel follow a Neustadt-Uhlenbeck process that, as you know, it means just a relaxation in a well. So at long time, each pixel relaxes in its own well. And so what you do is you transform the statistics of the pixel in white noise, because each pixel becomes just a Gaussian variable at long times. So in practice, what happens, so mathematically, it means that you have a certain initial probability distribution. You run, let's say, the probability distribution of images of dogs, for example, whatever this is. And running this SDE, you transform this, you convolute this with a Gaussian. This is just a solution of this equation. And at long time, so what this does is that transform nice images just in white noise. So for the moment, you didn't do anything smart. So what this diffusion model learn to do is what they learn to do the time reverse process. So here you transform a probability distribution, complicated, that you don't know, in a probability distribution simple, which is white noise. Now imagine that there is a process that is just a time reverse process that brings you back in time. So now if I give a new white noise configuration, I run the process and I get a new element of the original probability distribution, so a new image of a dog. So I don't know if you saw this movie, Tenet, it's science fiction, but this is exactly what they do in this case. So diffusion models learn really how to go backward in time. So to go to time reverse this process. So how they do it? Well, there is a theory, which is, well, theory is stochastic process. So if you have this Langevin process during the forward dynamics, there is a backward process, a backward Langevin process, which is just written like this. So you have, instead of having minus xi here, you have plus xi. But then the important thing is that you have a force field here, and this force field is called the score. And if you choose, I mean, if you take this force field equal to the grad of the log of the probability distribution of time t, then this will bring you backward in time. So let me maybe be a little bit more clear. So what is this pt of x? So you have this original process, which is forward in time. At a certain time t, you get this pt of x. So now if you want to go forward in time, well, going forward, sorry, if you want to go backward in time, what you have to get at the time tau, when you go backward in time, you have just to read what is the probability distribution that you had along the forward process. You take the log, you take the gradient, and this gives you the force field to go backward in time. So if you do this, so this is just an example in 1D, this will be the forward process. You start from some sample, take from 2 Gaussian, you run Neustadt-Uhlenbeck, you get Gaussian sample, and then you take new Gaussian sample, you run backward with the correct force field, and you get new sample, which comes from the original distribution. Okay, of course, these are mathematical identities. The problem is that in general, this force is a very complicated object, and you don't know it. The only thing you know, you have sample. And so what diffusion models do is that they learn using the deep network, they learn this force field. So you use a model which is based on deep network, and you just regress this force field. Now you don't use this cost function or this loss function. You can just transform this in something that you can evaluate in experiments, which is this. This sum here will be the sum over all the forward trajectory. So at the end, so the summary is that just using the forward trajectory and evaluated quantities during the forward trajectories, you can learn what is the force field to go back in time. And now once you have learned it, exactly as I explained to you, you take a white noise, you run the Langevin equation backward, and you get new images or new sounds or new videos. And this is exactly how they work, these models. All right, so and the nice thing also from the physics point of view is that, of course, this idea of using this trick of going backward in time was something that came from different, let's say, ideas and different fields, but there was a paper which came from physicists, really based on out-of-equilibrium ideas from out-of-equilibrium thermodynamics, that was very influential in this field. Now, okay, so that's, let's say, the theory. This is what I hope that Eric would have covered before me. So now what I want to show you is that using, so while in statistical physics, we thought a lot about out-of-equilibrium dynamics. And so using ideas from statistical physics, you can try to answer main questions and phenomena that people found in this model, at least to give some new perspective. So the two questions that I want to address today. So the first one is, well, imagine that I take images, let's say images of cats and dogs, and then I run this forward process. I learn this force field, and then I run the backward process. During the backward process, it means that I start from white noise, then I have trajectories, and somehow these trajectories, at a certain point, they have to, quote unquote, decide to give me a cat or to give me a dog. So how this formation of structure happens. So this is, I am going to study this in the case in which images have really two different classes, but in reality, this is a more general problem. Of course, an image has some big features and then some sub-feature and so on and so forth. So for example, here, there is a cat, there is a dog, and there's a cat, but then there are different kinds of cats and different kinds of dogs, and so on and so forth. So this is an example in which you have just two very different features. But in principle, you could think that there are many features. And the nice thing is that you will see this phenomenon, how actually the formation of classes takes place during this out-of-equilibrium backward process, is going to be related to, well, a dynamical transition out of equilibrium, so something in physics. Then the other problem that I want to discuss is something that is central in the field, and it's already, I mean, it's still an open topic in which is very much discussed, and I will just give you a perspective on it, which is memorization versus generalization. So now what happens in this model? So this is really an example of, imagine that I have, so here I have images of, I think, conference room and churches. And so here I take a state-of-the-art model, I train it on 200 images, like this. So, and then I just run the backward process and I get new images. So this is an example. And then I look in the training set, what is the closest image, closest with that to distance, to the image that has been produced by the generative model. And what you discover is that the model didn't produce a new image, just produce an image that is in the training set. Same thing here, same thing here, same thing here. Okay, so now here in the model, it means is in what we would call a memorization phase. So it's not working. You want the model to generate, I don't know, new songs or new images, and it's just not producing exactly the images that we put to train it. Now you take the same, let's say, diffusion model, the same deep network, same number of parameters, same way to train it, and you just increase the number of data in the training set. So if you use 1,000, you will still get memorization. And if you crank up the number of data and you arrive at 40,000, in this case, you start to see that you generate images which are not in the training set. So somehow, increasing the number of data, the system goes from a memorization phase to a generalization phase. And this is not just, I mean, this is an example that we did, but this is something that you even find in industrial models, which are trained in massive data set. And it's really, I mean, it's really a problem in theory, because theoretically, to understand why this model works, you want to understand how this generalization phase is possible. But it's also, of course, a problem in practice, because, well, in all companies, if they produce, I don't know, a song that, I mean, it's in their training set, so it's a very famous song, they're in big troubles. All right, so, well, this memorization, generalization always happen with a crossover at a certain number of data in the training set, and this number actually can depend on, well, the deep network that you have used, the kind of data that you use, and the training procedure, but it has always been observed. And you will see that, I mean, this memorization transition is actually, we will see that is related to, at least our perspective, to something that happens in physics, which is the glass transition and slow dynamics. There are some ideas that come from these topics that can be useful. Okay, all right, so let me go very quickly to what we can do in theoretically. So one first approach that we follow is to first take models that we can solve exactly, which is what we do in statistical physics, which are models which are simple enough to be solved, and which are a caricature of what of the kind of complex system that you want to describe. So what I want to describe now, if you remember, is in the first case is how the model decides to produce an image of a cat or a dog. So this means that the probability distribution, in a sense, is formed by two different peaks. One is the peak related to, let's say, of images of cats, and the other is the peak related to images of dogs. So one way to make a very simple example of this is considering what is called a Gaussian mixture. So you take data which some probability P comes from a Gaussian, which is centered in D with a covariance, which is the identity, and with probability 1 minus P comes from, well, another from a center, which is minus V with the covariance, which is the identity. So the model is just two Gaussian mixture. Another simple model, this is something that says this will be the Ising model of computer science. If you take instead the Ising model of physicists, so if you take a Curie-Weiss model in which you have Ising spins fully connected, you take it at low temperature, so below the transition temperature. So this probability distribution, which is where it's an Ising spins, and we know that it's a probability distribution which has two lamps, one on positively magnetized configuration, the other one's on negatively magnetized configuration. Now, these two lamps in one model and the other are the two classes that I want to focus on. And so now we are going to play the game of, we're going to see how a diffusion model actually starting from white noise is going to produce either positively magnetized or negatively magnetized configuration, or configuration which are in one Gaussian or the other. So in order to do this, to study this, we consider a high dimensional limit. So which means that this vector it's very high dimensional, which is the case of real data. Images are very big. We take a number of data which is large, and then we are going to do an hypothesis which we call the exact empirical score hypothesis. So we consider that the deep network that we use is powerful enough to learn the exact score. So which means that what I mean by exact score, so I mean that I start from a probability distribution, initial probability distribution, and I know what the score is. It's the grad of the log of pt of x. So we are really studying the exact process. Then there is something else that one would like to study, is that if instead I use a deep network to learn this, maybe I'm not going to learn it perfectly, so there is an additional difficulty. But for the moment, I don't consider this additional difficulty. I just do exact. I just want to study the exact backward dynamics and understand how it goes. All right, so so this means also that pt of x here will be the convolution of the Gaussian with the empirical distribution, which is the sum over the sum of all the delta peaks, each delta peak around each data. All right, so I have to cut a long story short. So what we found is that, so here is an illustration, just two-dimensional, in reality in very high dimension, of the trajectory during the backward process. So the first thing we find is that there are different dynamical regimes. So there is the first dynamical regime with the transition, at which indeed you have formation of classes. So what happens is what you see is the trajectory. At the beginning, of course, you start just from white noise. And then while they go, what happens is that they follow a Langevin dynamics in a force field, which actually you can rewrite as deriving from a potential, but this potential changes with time. So at the beginning is just a well, and then it forms actually two wells. And then these two wells becomes deeper and deeper, and they go farther and farther. And this is what actually bring the trajectory away and bring some trajectory on one side, let's say to the cat, and one other trajectory to the dog. And this in the high dimensional limit is a true dynamical transition that what happens on a time scale, which is 1/2 of log in this case. So here is the formation of classes is really related to the fact of that this force field actually create an effective dynamical potential that brings the trajectory away. And after this time, the trajectory really separates. So what I mean is that the trajectory that are going to, let's say, this lamp will never, with probability 1, go to the other one. So it's a real transition. So the trajectory after, in this regime, are really committed to the class in which they're going. All right, so this is the first result. Of course, this was found in simple models, and then you can ask, okay, what about, can we translate what we found in simple models to something that we can test in practice? And in practice, what you find is that the time scale at which this transition should take place is 1/2 of log of lambda, where lambda is the largest principal component of the correlation matrix of the data. So it's something that if you have the data, you compute numerical correlation matrix, you look at the largest eigenvalue, take the log, you take 1/2, and this should give you an estimation of the time at which this transition takes place. And I will show you numerical experiments later. All right, so now what about the other phenomenon, which is the memorization versus generalization? So now this happens later. So what happens, I told you before, is that first you have this trajectory, just white noise, they didn't decide where to go. Then at some point there is the transition. And so here, let's say one trajectory is decided to give me a cat and the other one to give me a dog. And then what happens is that along the trajectory, you refine more and more the image. So in this regime 2, the image becomes more and more defined, less and less blurred. And then what happens is that we find that there is a regime 3 in which actually the force field starts to really point toward the data. So the trajectory and this regime 3 will just hit and go toward one data in the training set. And the difference between regime 2 and regime 3 is that in regime 2, the score or the force field is the one that you would have if the number of data is infinite. Whereas in regime 3, you really feel the fact that you have a finite number of data and that the force field is correlated with the data in the training set, and it really brings you at the end toward the data. And now this transition can be understood using actually methods from disorder system. So what happens is that here, if I look at the score is the log of PT of x, and then you have to take a gradient. Now, what is PT of x? Well, it's just the noise version of the delta peak, which correspond to the initial probability distribution. Now, well, if you look at this sum, if you rewrite it in this way, well, it's like if you had this some quench disorder. The disorder comes from the initial data in the training set, and this is something like a partition function. It's a problem that has been studied a lot in disorder system. It's called the random energy model, and it's known that this actually has a transition in which its partition function is equal to its average, which means that you find the same thing that you would find when you have an infinite number of data. And then instead, there is a transition at which this is just correlated with the A mu that you have here. And now this transition is like a glass transition. And let me explain pictorially here what's going on. So when you start during the forward process, or you look at the end of the backward process, so you have the data, you put a little bit of noise around the data. So you just have that PT of x are just peaks around the data. And so if you think at the probability distribution, let's say they look like this. This is not what you would like to have. What you would like to have, and that you would have if the number of data was infinite, would be something like this, in which you feel an entire manifold. Now, sorry, I should put it here. This is what you would get with an infinite number of data. This is what you get with a finite number of data. Now, when you go forward in time, or you go more at the beginning of the backward process, these balls actually becomes larger and larger. And at a certain point, they fit completely the manifold. And so actually, the PT of X that you have, which is the one that you have in this regime 2, is actually equal to the P true, to the true one, the one that you would have with an infinite number of data. And this resembles, if you think this in terms of occupation of the configuration space at different temperature, the kinds of energy landscape that you have in glasses, it looks like that this regime 2 is like the high temperatures, and this regime 3 is like the low temperature, and this would be just the ideal glass. And within this formula is exactly what happens. All right, so now if you follow this idea, this simple idea, you can actually find a criterion to understand when this transition takes place. Well, the transition takes place when these, let's say, balls, which are just this, is the space around, I mean, it's the space covered by the Gaussian around each point, is going to fill all the manifold. And so it's just a volume problem counting. So what is the volume which is filled by this PT of X? Well, it's the number of data times the volume filled by Gaussian. In high dimension, this is just the exponential of the entropy of a single Gaussian. What's the volume filled by the true probability distribution? Well, it's the exponential of the Shannon entropy related to this distribution. And now, when the transition takes place, when this volume is equal to this volume, and so if you equate the volume, you take the log, you find actually that the transition takes place when you have this entropy condition. This is the entropy of the true distribution. This is the entropy of a single Gaussian. And here you have a parameter, which is the log of the number of data divided by the dimension. So this is general, but you can look whether it works or not. It works in simple models. We can compute it exactly, and I will show you that it works also on real images. There is one interesting thing is that you see here you have log of n divided by d. This is the parameter that actually can shift the time at which this happens. So if you want that this time is pushed toward the beginning, so you want to shrink the memorization regime, so you have to have a lot of data, but a lot means really a lot. It means exponentially in the dimension. So this means that there is a curse of dimensionality. So you will have memorization except if you use an exponentially large data set. Okay, so that's what we find. And so at the end, so this is the conclusion. Dynamical regime, you have 3 dynamical regimes. If you, in high dimension, if you study the exact dynamics along the backward process. So now we can test whether these things are just things that we find in simple models or whether are things that we will find in real images. So what we did is we take models, let's say state-of-the-art model, kind of, yeah, state-of-the-art of 2020. And then we take images, I mean, simple images, but different kinds of images. So minced, that was already discussed. We always take 2 classes to make the connection with what we did. So here you have a panda and seashore, here you have 1 and 8, here are horses and cars, and so on and so forth. And then we are going to test exactly the what I told you before. Okay, first test is there this transition that we call speciation transition along the backward dynamics? So in order to study it, what we are going to do is the following. So we do the backward dynamics, we have the trajectory, and at a certain time of the backward dynamics, we clone the trajectory. So we have 2 trajectories that evolve with 2 different noise. Now, if there is a transition, indeed, if we clone before the transition, well, I mean, the trajectory have not committed, so one trajectory can go to one class and the other to the other class. If I clone after the transition, well, the 2 trajectories will always go to the same class and this go to the same class. So we just, I mean, do this in practice. We know the score for these images, we do the cloning, and we compute in the numerical experiments the probability that the 2 trajectories end in the same class, and this is, you see, if I clone at the time which is close, which is below TS, where TS is computed as 1/2 of log lambda, as I told you, then the probability goes close to 1. So indeed, the 2 trajectory goes to the same class. And if I clone before, then the probability is 1/2, so they can go to one or the other. And then, so this is for different images. And you see that you can kind of rescale actually the different curves if you use this TS, which is different from different kinds of images. And this is what you find in a simple model that you can do analytically. Okay, so this tells you that actually the phenomenon is there, and even that this estimate is quite good. And then there is actually now a very other nice way that has been developed first by Benjo et al. And then as studied by the group of Mathieu Viard, which is U-turn experiments. So what you do instead of cloning along the backward process, you start from an image, you go along the forward process, and at a certain point, you do a U-turn. So you come back, but with a different noise. So again, if you come back before the transition, you will go to the same kind of image. If you come back after the transition, then you will go to the other class. But they did it actually in a case in which you have many classes. So what you see here, you start from a leopard, I think it's a leopard. And so if you go a little bit forward in time and you come back, well, you get the same leopard, but actually the color of the eyes is changed. Then if you go a little bit farther and you come back, you still get the predator, but it's a wolf. And if you get even farther and you come back, you get the butterfly. Okay, so you see here, you don't have two classes. You have, let's say, two big classes and then subclasses and subclasses. And you see this phenomenon of branching during the backward process. It's another way to see it. All right, so this is for the speciation transition, for the dynamical transition related to the formation of classes. And now what about the memorization transition? Now, what we did is we consider a case in which we have not many images, and we have a very powerful model, so we can be quite sure that actually the model is learning the exact score or something which is very close to the exact score. At least this is our hypothesis. And then we compute numerically the memorization time. So how we do it is that along the trajectory during the backward, we look at what is the closest image in the training set. So when you are, let's say, in regime 1 or regime 2, the index of the image is going to change a lot because the system is not, the trajectory is not correlated to any data. But then at the end, when the trajectory goes toward an image, then the index will fixate. And so this is what you see here. So these are different trajectory, and you have, well, they fixate at different time. So you can compute the average time at which you have the memorization transition. And so you enter in regime 3. And then what you can do is that you can compute actually this entropic criterion to get what is the time scale from theory. And this is what you get. So this is f of t. So if we plot f of t and we look at when it goes to 0, these are different kinds of data set. These are face of celebrities, men and women. And this is ImageNet, maybe Eastman and Seashore. And so and here you see that when it goes to 0, it's close to, well, this is the, this thing here is where is the estimate that come from this. So this is the estimate which come from the numerics. This is the estimate which come from the theory, and you see that it's quite close. And so again, we don't pretend that it's exact, but it's a good estimate actually that indeed there is a memorization transition, and it happens at the time scale which is close to what we have from this argument. Now there is one important thing before is that. In this case, we are considering very few data. And with very few data, we are saying, okay, at the end, the system will always memorize. Now, in practice, the system don't memorize. They use a lot. I mean, you are in a regime in which they use a lot of data, and they generate new data. And so the question is now, because this would seem pessimistic, but what we did is that we make the hypothesis that the system is learning the perfect score, given the training set. And this is clearly not what's happening in real life. And so the question is why diffusion models don't memorize in practice. And so this, I think, is a very interesting topic, and there are several possible answers. And it's an active topic of research, and I will just tell you what is our answer, because again, it's related to a nice problem in, I think, in physics and in out of equilibrium physics. So what we find, first from numerical experiments, and then we have simple model, is that it's related actually to the training dynamics. So the training dynamics, what does it mean is that you have this cost function that you have to minimize. So it's just like you minimize by gradient descent. So you are in very high dimension, you have to minimize and go down this lost landscape. And actually, the global minimum of this landscape corresponds to the score, the force field that memorize. But somehow the system doesn't reach this global minimum. Or it could be that it doesn't reach because maybe it's not powerful enough. So actually, there is some kind of regularization. But what we find instead is that it's not like this. So this is what happens during the training time. So if I stop the training time, certain time tau, and then I generate image. So this is the property of the image. So if I stop the training time too early, so I'm just going down the lost landscape, I just very far from any kind of minimum. If I stop there, I produce new images that are not good. But now if I let the system go, then the quality of the image will be good, and the system will not be in the memorization phase. If I keep training, at a certain point, the images are still good, but they start to be actually in the memorization regime. So you start to reproduce the image in the training set. So what we find is, in terms of, let's say, dynamic descent in the loss landscape, is that the loss landscape has a kind of bottom, which is very flat, but it's not zero. And so when you go you start from the initial condition, which is here, you arrive here, you stay here a very long time. Here, the system is in a solution which corresponds to generalization. But then if you really wait a very long time, at the end, the system finds a global minimum, which corresponds to generalization. And now the time scale, this big time scale over which you stay, you generalize well, and you have good quality, increase with the number of samples. So the more sample you have, the larger is this time scale. This is why actually many systems, you don't even see the memorization, because the number of samples that you use is so large that you stop at a certain point in the training, and the system is in this phase. Now to see it, let's say, in a more real space way, so what happens is that this core field or this force field is very irregular when you have a number of data which is fixed, it's not infinite. So here in this example, the gray line is the score. So it's just a one-dimensional example. The dashed black line, it would be the score, which corresponds to an infinite number of data. And what you see, the yellow is the guess of the neural network at the beginning of the training. So it's very different from both the gray and the black. And then you go down in training, during training, and you find that you see the yellow just match the black. So you stay very close to the generalization score for a long time along this period here. But then if you wait long enough, actually, well, the yellow will be able actually to change and to try, and it will start actually to reproduce the peak that you have here, and reproducing the peak. If you use the score, you will actually reproduce the data in the training set. All right, so this is something that you can read more in this recent paper, and that was also studied in the group of material. Okay, so now I can conclude. So what I wanted to show is that these diffusion models are, I think, interesting in many ways, but for physicists are particularly interesting because they are connected to a problem of out-of-equilibrium physics. And we can also, I think, say several things based on the concept and methods that were developed in the field of out-of-equilibrium physics. So in particular, I show you that there are three different dynamical regimes along the backward process. There is the first regime in which actually you go from white noise to a point in which trajectory commit to a given class. And actually, if you have subclasses, then while they commit, you have a sequence of transition. And then there is a regime 2 in which actually the details of the images are formed, so it becomes less and less blurred. And then the regime 3, actually memorization takes place if you use a perfect score. And I show you that there is a general numerical criterion to get the transition, but also I explain why actually in practice this doesn't happen. So the understanding actually the three dynamical regimes gives you interesting perspective also. Yeah, understand? Perspective on application. So for example, while in application you could try to decide whether you want to go, maybe you want to be very precise in this regime and less precise in this one. And this is something that you see. Imagine, for example, that you have 1/3 of cuts and 2/3 of download images. If you want to get this 1/3 and 2/3 right, you have to be very precise here. And if you are not good here, maybe the images will be good because, I mean, the big part of the image is generated here. But once you are here, I mean, you go get a dog or a cat is decided. So the fraction here is fixed. So if you get the fraction wrong here, that's it, you get this fraction wrong. So this tells you that as a guideline for application, you can reparameterize time in order to be better in some regime. And this is something in which we work with Eric. And then actually, and this I don't have time to tell you, but actually all these ideas are allow us to find new way to do classifier-free guidance. So classifier-free guidance is something that you do, for example, when you do text to image. So it's when you want to produce an image which is conditioned to a prompt. So for example, the angry bird that I told you at the beginning. So you train the system in such a way that I ask the system to produce something that I want. And actually what they do in practice is something which is really quite not related to the theory, and actually we explain based on this dynamical regime why it works. And we can say thank you.
Thank you very much for actually keeping so well to even the time with including the extra bit. The paper is now open for discussion. Emanuela. Oh, microphone.
Very interesting. And that it makes more sense to think in terms of it's a going beyond the white noise and having the noise that you can use to design or to understand better the transitions in terms of what happens to
Yes. And I don't know whether Eric is going to tell something about this, but actually the idea of, I mean, using the distribution, so you don't need to go to white noise necessarily, and so you can indeed decide not to go to white noise, and also change the noise that you use, along the process in order to optimize something. And typically, to optimize is, for example, the number of steps that you want to do to go back, or the quality of the image. And so this, I think, are interesting questions, but they are not, I would say, are really topic for research right now. But yes, the answer is yes. There.
Other questions? Yes.
So if you get close to this final regime where things are being pulled down into the trains, and you disturb them at that point, do they still get pulled down into the trains?
So how you disturb them?
Well, one way would be to switch to a different training set. Then, so do the whole thing twice. You get all the way towards the memorization, what we call it.
Yeah.
But then you do it with the other training set.
Yeah.
So you're actually something being pulled to a totally different set of individual images. And the question is, does it then get stuck in a good low noise, but original image, or does it still eventually find its way down into
I think if you really switch to another force field which corresponds to another training set, and you just keep that one, you will go to the data in the other training set. But if you keep switching, that's interesting. I think if you keep switching, I don't know the answer, but yeah, I mean, if you
it's
a kind of regularization.
The fact that you've got this basically very long waiting time to get pulled down into the training data. But okay. Yeah. So basically anything, if you put it in that final region and wait long enough, will turn into the training data.
If you use the correct force field, because in a sense, I mean, the only thing that the model learned has seen is this original distribution of just n images. So if you really does the job well, this is what it has to reproduce.
Yeah. One final question. Yes.
Yeah, thank you. Nice thought. So how understood it is, you start from the white noise and time learn the time reverse time operator for the Landry equation. But you then just go from the white noise until it eventually comes out an image. You don't take certain steps and then compare it against sort of the type of image that you want. Is there a reason that you do that? Would that somehow improve training, or as in, if you went back to like maybe the second slide? Yeah, that one. Forwards. There, so you go from the white noise, but you want to go backwards. But how I understood it is, you don't take a step, like running the time evolution backwards, and then compare it against the image that you want.
You don't want an image. You want a new image.
Yeah. But wouldn't that help training? I don't know, maybe I didn't quite understand, but wouldn't that somehow improve the training?
I'm sorry, doing what? Comparing with with the image. So I mean, trying to put in the force field something that repels the trajectory from the training set. Is this the question?
No, it was more just if you could somehow improve the training if you compare against the type of image that you want, not that you want it to spit exactly
okay.
what you want.
Well, I see.
Something that's similar to.
Yeah, so this idea of conditional free guidance that I was saying at the end, yeah. So it's a little bit going this sense. So it's, imagine you say, I use the force field that I learned, then I push a little bit toward the class that I want to do. So this is what I do in practice. At the same time, it's a little bit, it's bad in the sense that there is a nice mathematical theory. So if you use something which is not the force field that you're supposed to use, you are not going to generate the distribution that you want to do. But it's what they do. What they do is that they give an extra kick to go in the correct direction.
I think, Roger, I think you'll have to ask offline, sorry. And thank you very much.